Hello, everybody, and welcome back to Creation Myths. Just a quick little intro here before we get to the main video. What I'm going to show you here in this video is an approximately hour-long conversation I had with Rebecca from Examining Origins on her Examining Origins channel, despite my frustrations with that whole thing. In spite of myself, I found myself listening to one of her shows while I was doing other things, and then I decided to jump in to clarify some of the stuff that I was hearing because people were making points, including a creationist guest prior to when I was on, were actually making arguments. This creationist was making arguments that were against creationism, against the thing that was being talked about, which was mitochondrial mutation rates versus mitochondrial substitution rates. And so I decided to jump in and clarify a few quick things. And of course, those conversations are never quick. So I ended up chatting for about an hour. And the main substance that we talked about, as you'll see, it's the mitochondrial most recent, or time to most recent common ancestor, and in particular talking about the phenomenon of background selection. Now, some of you watching this may be thinking, Dan, why did you do that? I know that you don't like that whole thing on the format of those shows and you find it very frustrating, and all of that is true. And in spite of myself, I think it's important that people have these conversations, in particular, where there are creationist audiences and where basically where creationists go, because the fact of the matter is a lot of creationists don't get outside their bubble. So if you're going to get the information to the people who don't know it, you need to get out of your comfort zone in terms of where you're willing to appear and where you're willing to have conversations, and in terms of who you're willing to have conversations with. Fortunately, Rebecca is a very pleasant person to have a conversation with, even if those conversations are often very frustrating, let's say. But the other side of that is it's important to have somebody there who is conveying accurate information for the people who stumble upon it who aren't sure. There are people on the fence who could get swayed either way, and if we, the pro-science side, just kind of opt out of participating, then those people only get exposed to the misinformation coming from the professional creationists laundered through the amateur creationist YouTubers, and that doesn't help anybody. So for those reasons, I jumped in the show, had the conversation, and do I expect that anything there is going to result in any long-term change in Rebecca's mind? No. Do I expect any changes to any of the regular kind of young Earth guests and viewers that also participate and watch and comment on those videos? No. But maybe somebody sees it and the information is out there and it's helpful. And that's why I think it's important that people do it. And especially for scientists, we shouldn't opt out of having these conversations. So I think that is, I think that's enough of an intro here. So let me just show you the video. One last thing I'll say is I apologize for the god-awful quality of my camera. The sound was mostly good throughout with just a couple little hiccups, but the camera quality is terrible. I did manage to track that down to StreamYard hating Chrome, and when I do it in Firefox, it's fine. So going forward, the quality should be fine anytime I appear on a live show using StreamYard. We'll see if that continues to be the case, but I've tested it a bunch of times, and hopefully this is the last time I appear as a Minecraft character on a live video. So thanks, everybody. Hope you enjoy and maybe learn something from this conversation.
And I will bring on Dr. Dan. Hey, Dr. Dan.
Here we go. Hi, how are you?
Good. How about you?
Okay, I'm good. Let's see. I'm interested to see if I look like a square of pixels or if I look like a person.
Yeah, you're pixels for me right now.
I look like a square of pixels. I don't know why that's happening.
Fine.
I just did a speed test like 10 minutes ago. I'm on a really fast connection. StreamYard just hates me. I don't know why. Whatever. Anyway, so I want to pick up with this Neanderthal thing because I think we're overcomplicating it here, and I honestly have no idea all that stuff Junior was drawing. I couldn't follow what he was saying. But in terms of evolutionary assumptions in the Neanderthal stuff, it's super simple. There are no evolutionary assumptions because all we're doing is sequencing the DNA. We have the DNA and we're sequencing it, right? So you sequence the mitochondrial DNA, and in Homo sapiens, right, all living humans, the maximum divergence between any two people, right, the number of mutations that separates the two most different people is about 120, right? And what the young Earth argument is, we can account for all of those mutations using the Parsons pedigree rate. We can account for all of those mutations in 6 to 7,000 years, somewhere in that time frame. Is that a fair representation of how we do this?
Yes, according to that study.
Okay. Mm-hmm. So if we all agree, if in the young Earth model, that Neanderthals are descended from Adam and Eve, and in general, the consensus with, answers in Genesis and whoever else, is that Neanderthals are actually a post-flood population. So they're descended from Noah's 3 sons and the 3 wives, right? So Neanderthals share a common ancestor with humans, according to the young Earth model, right? 4 to 4,500 years ago, somewhere in that range, whenever the flood happened, right? Now,
or 5,500.
Yeah. So the reason this is a problem for the young Earth model is that we can sequence the Neanderthal mitochondria, right? And we find that they're way more divergent than any two humans are today. There's no evolutionary assumption in that. We just sequence their DNA and go, wow, this is way more different from that person or that person or that person than any of them are from each other, right? There's just more differences between their mitochondria and any of our mitochondria than there are between any two living people, right? That's the data that we're working with here, that Chris was pointing out, and Junior actually pointed out the exact same thing, right, with his figures. That's the data we're working with. Are you okay with that? Do you accept that those sequences are valid?
Yes, I do.
Okay, so here's the math then for why this invalidates the young Earth model. We don't have to have any evolutionary assumptions. We don't have to go back 800,000 years. It's just we have a certain amount of variation that exists in Homo sapiens today, and if you use the preferred young Earth rate, you get your most recent common ancestor at the earliest time you can, right? At like 6 to 7,000 years ago, which is where you need it to be. You can't do 10 or 12 or 15 or 20 or whatever. That's outside the timeline. Now, some young Earth models can go to 10, but like mostly it's in the 6 to 7 range, right? So if you have to double or triple the amount of divergence you have to account for, even using the same rate, you necessarily have to move that common ancestor backwards in time, right? So if you converge at 7,000 years using the Parsons rate and the 120 differences, then now you have to account for 250, 300, 400 differences. Now you're not within the 7,000 year time frame anymore. Now you're back at 15, 20, 25, right? You necessarily have to move that most recent common ancestor backwards. That's it. That's why Neanderthals invalidate the young Earth model. You can do everything the same. You can do all the math the same, which, to be clear, is wrong. But that doesn't matter because the additional divergence you need kills the model. Also, I think I'm frozen on YouTube right now, so I don't know if anybody.
Oh, yeah, you're frozen, but that's okay. I can still hear you. And you know what? This might be a good objection. And so let me give credit to Dr. Thompson. He might have brought a good objection. You might be bringing a good objection here. The thing I was like getting really, fighting back on with Dr. Thompson is when he started bringing in 800,000 years and that kind of thing. So, this is something, it might be a good objection, and I would like to look into it. I'm trying not to make promises about this because I have like so many things to look into right now, but it might be a good objection. And it is something I'm curious to look into.
Yeah, let me put it this way. Everybody accepts that the Neanderthal sequences are valid, right? Except for one person, and that person is Nathaniel Jeanson, and he's the person who has done this math for the Young Earth Ministries. He's at AIG, but everyone else basically just does his math. Everyone, cribs his work. And his response to Neanderthals is to ignore them. He says they're not valid. His reasons for that are wrong, and it doesn't matter. It's beyond what's relevant for tonight. But he recognizes that if you include the Neanderthals, it does violate the time frame. And his response to that is the Neanderthals are invalid. We don't have to include them. Now, other creationists like Dr. Rob Carter have said, no, the Neanderthal DNA is perfectly valid. We just have to have a mechanism to explain it, right? And other creationists have proposed things like, well, there's a lot of radiation during the flood, and that accelerated the mutation rates or something. Like, there have been, I think, kind of silly proposals to explain that. But in the professional young Earth community, there is a recognition that if you take the calculations that are done at face value, with the Parsons rate, with the Ding rate, which whatever rate you want to use, and extrapolate those backwards, and you include the Neanderthal divergence in there, you're well outside the young Earth timeline.
Okay, I'm going to bring this one to my creation advisor.
Who's your creation advisor? Because this has a thing of like, you've got a bunch of like, kindergarten teachers sitting around going, triangles have three sides. You're like, I'm going to bring this to my toddler and see what they say. Like, who's your creation advisor, and why do they get to like do math differently than how it's done in the real world? I want to know who's your creation advisor.
Yeah, I don't know if I want to reveal my creation advisor right now, but if my creation advisor didn't tell me this is a problem, then I would be like, and it is a problem, I'd be very surprised. But
I'd be surprised too if they admitted it was a problem, because yeah.
Okay, well, it is something I'm gonna follow up on. But I'm actually
with your creation advisor, though. Do you understand like why that's a problem, Rebecca? Like, do you understand the epistemic bubble that puts you in? If every time you hear new information, you have to go to, I have to ask the person who agrees with me.
No, I mean, I don't take his word for everything. Okay, I fact check him, and I find out that he's usually right. In fact, I can't think of a time that he's been wrong. Okay. So it's not about, just taking one person's advice. Actually, I'm a very skeptical person. Even the people I trust most in the world, like my husband, he gets mad because I don't believe what he says automatically. Okay. And I trust him very much. So even the people I trust most in the world, I don't take their word for anything. Okay. I am very skeptical. So, it is something to look into, but I'm actually surprised that you challenged what I said. I mean, you wanted to go down this route of talking about Neanderthals when, you've had an issue with these mutation rate things before with, the pedigree versus phylogenetic studies. So do you have anything that you want to challenge that I said?
Oh, yeah, sure. So first, let's just real quick. This is not like to start a debate about Parsons, just straight up. If you go and read the Parsons methodology, not the abstract, the actual methods in the paper, they didn't weed out somatic mutations. Like, just straight up, like, if you disagree, go to the methods, find the line where it says we did that. Because they didn't. Just straight up, like, that study includes somatic mutations. Just want to clarify that. There's nothing else to say about it. It's just like, that study includes somatic mutations in the data, like, just to be clear. But the thing that I'd be happy to talk about background selection for a minute, because this is something that is really important here, because what creationists do is they cherry pick the control region, right? Which is only about 10% of the.
Before we go into talking about that, I'm sorry to interrupt you, but before we get off the somatic mutations, because I don't want to forget about that. So you might be right about the Parsons study, and I don't remember off the top of my head if they had a methodology. So I'll take your word for it that they did not weed out the somatic mutations. But do you agree that there are lots of pedigree studies that do take account and try to weed out somatic mutations and still get a fast rate?
Do they try to weed it? You would have to give me a specific study for me to answer that question.
Okay,
I have a folder
could be
full
wrong
of them.
about I could be wrong. I don't remember exactly which one. I know Hayer, I think, did. Santos did. There's several that did actually try to do, and I might be wrong about hair, but there's several studies that I read where they specifically discussed that they were taking precautions to weed out somatic mutations by testing multiple siblings and multiple
Right.
grandmother, mother, daughter. So
Right, but if they test, and this is what Parsons does too, if they test, and they do this in Parsons with the Amish family specifically in Figure 2, I think it is, where it's grandmother, daughter, granddaughter, right, in that figure. And what they do is they count the mutations at each step in that pedigree, and they're still therefore going to catch somatic mutations when you do that, because in order to weed out the somatic mutations, you have to do multiple generations. That's the point. If you can do 3 generations, so you can do a great grandparent, you can do 4 generations. If you sample each individual and count all the mutations, you're going to catch somatic mutations. In order to weed them out, you'd have to sequence grandma and granddaughter and not count the mutations that we find in mom. But in Parsons, they explicitly don't do that. They don't do what you would need to do to weed them out.
okay, I mean, and I'll take your word for it on that. But I mean, are you saying um, are you saying there are no studies that like take this into
So,
account?
in a single generation pedigree, it is very difficult to weed out somatic mutations because in none of these studies, to my knowledge, are you sampling the germline. You're sampling somatic cells, right? Now, right?
Right, but you're sampling multiple generations.
But if you're going from like grandma to daughter to granddaughter, and you're counting all the differences at each stage, that's including the somatic mutations.
Right, but they're going back further than that based on genealogical records and comparing divergent lines.
So
Right.
why is
So
it?
they're able to do deeper pedigrees because they're going back.
Yeah,
They may
and
not be able to test the blood of that person that they diverged from, but they're able to look back. They're able to look at the sequences of multiple lines
mhm,
with the genealogical
right.
records.
Right, and when we do that, and again, this is getting, I want to get to background selection, and that'll be quick because it's pretty simple to explain, I think. But real quick before we get to that, to be clear, when we do that kind of thing, those are the types of studies that get criticized as having evolutionary assumptions in them when I cite them, because that's like the Sudyal, Tristan da Cunha study, that's the King 2014, Anne of York, Richard III study, right? You just described the exact methodology that I like to cite. And when I cite it and say, look, these are directly known dates with known lineages, and we're sampling from that known genealogical ancestor, and we get a rate that's consistent with a mitochondrial Eve 100,000 years ago, what do people say? They say, oh, evolutionary assumptions. You just described the exact methodology I use, and when you use that methodology, you don't have to go back very far. You go back to the 1800s, you get the slow rate. Yeah, like
Okay,
what you
well,
just
it
described is
wasn't
is the
just
correct way to
Sudyal.
do
It
it.
wasn't just Sudyal that did that
Well,
accounted
there's a
for.
bunch. There's the Norfolk Island one. There's a bunch of studies that do that, and they all get numbers that are consistent with the mitochondrial Eve. The earliest you get is approximately 60,000 years ago, and the latest is approximately 200,000.
Okay, and that would be how many mutations in a generation?
It's approximately one mutation. I'd have to do the math real quick, but it's approximately one mutation every, I want to say 30-ish, I think gets you to about the 60,000, I think it is. I'd have to go back and look. But I
Well,
think it's
Parsons
about,
was
yeah.
one mutation for 33, and that gets you to the
But
6,500.
but Parsons was only looking at the control region. He wasn't looking at the whole genome, and because the genome is non-recombining, you have to look at the whole thing. You can't isolate the control region.
Wait a minute. Then why do most of the studies just use the control region?
Because the control region is where most of the mutations are because it doesn't have the genes. So you can survive the mutations there.
Right. But the problem, and I mean, I'm surprised that you're saying that
Yep, keep
that the
follow the
whole
logic, keep going.
Well, I'm surprised that you're saying the whole genome, the whole mitochondrial DNA is good for sequencing, because
Yeah,
you're always
yeah,
complaining that we're not accounting for selection.
yeah.
And if we do the whole mitochondrial DNA, then we're going to
You're
have
accounting
a
for
lot of
exactly.
problems figuring out about
No,
selection
you
and
look
those
at the
kinds of things, right?
substitution rate of the mitochondria, and the reason you have to do this is it's non-recombining. Now, when you're looking at the nuclear DNA, you can look at individual regions because it recombines. So you can have individual regions that are disconnected to each other because of crossing over, because of recombination. In the mitochondria, it's non-recombining. So this gets us to background selection. This is perfect. This is why this matters, right? So let's look at this. Just think about the mitochondrial DNA as a clock, right? Think about it as a clock face, right? Now, the control region is a really tiny fraction of the mitochondrial DNA. So take from 12 o'clock to 1 o'clock. That's your control region, right? And then from 1 o'clock all the way back around to 12, that's the region where you have all of the genes, and it's super dense. There's almost no intergenic regions in that part, right? So you have a person, who has 10 mutations in their control region. And those mutations, they're in the region that doesn't affect the protein, so they don't hurt that person, right? Now, let's just say that person experiences a mutation like in their embryo, right? When they're in, during development, they experience a mutation in one of those mitochondrial genes. And that mutation is really bad because it means they can't do cellular respiration correctly. So they die, right? At some point they die and they don't have kids. So that one really bad mutation never gets passed on, right? So we don't see that mutation like over lots of generations, right? That's selection happening. Does that
Right.
make sense? We're okay
Yeah,
with that?
totally following.
Okay.
Yeah.
Okay. Now, when you lose, let's say that mutation happened at 7 o'clock on the clock, right? In that chromosome, it happened down here at 7 o'clock. What happens when that individual dies? What happens to the 10 mutations in the control region? Do those get passed on, or do those also go away?
Well, as you said, this is the background selection. It's linked together. It's gone.
So they go
Right.
away. So
Yeah.
would the rate at which those 10 mutations occurred be equal to the rate at which they achieve fixation?
Oh, okay. I see the point that you're making. Yeah. Okay.
That's background selection. So when you remove the very rare but deleterious mutations, right? They're actually not that rare because there's a lot of germline selection that we never even see. These are actually because it's 90% of the genome. But when we remove those deleterious mutations, you are removing the linked variation because the mitochondrial DNA is non-recombining. So even if those 10 mutations, let's say those 10 mutations, those are probably not the only instance of those mutations in the population, right? There's probably other individuals that have one or more of those 10 mutations. But because somebody with those mutations got a really bad one and that individual died without kids, those 10 mutations are now reduced in frequency in the population, and that increases the time it takes for them to achieve fixation within that population. That causes the mutation rate to diverge from the substitution rate.
Right. But that really doesn't explain that doesn't explain our observational studies of the mutation rates,
It
right?
does, because
obviously we're
they're too
not going to
short.
be testing the people who died out, right? Like if
Exactly,
they
right.
died out,
But
they're
you
not
can
going to
do
be
that, and that's why you use the multi-generation studies. Exactly. In one generation, you're necessarily only testing the people who survive, right? So there's no, you can't detect that effect when you're looking from mother to child, or from grandmother to mother, or from that mother to the next kid, because it's single generation steps, so you can't detect that effect. But if you go back 100 years or 500 years to a known genealogical ancestor, now you can determine, you can feel that effect, right? And that's why, just going back to Norfolk Islands, Tristan da Cunha, Richard III, just within the last few hundred years, right? Richard III is 1400s, it was Anne of York, right? So you're going back 600 years, that's short enough for that background selection to exert an influence. But one generation, you definitionally can't, right? Because if you're only, like you said, you're only surveying the people who are alive. But over longer periods of time, mitochondrial lineages will go extinct.
Okay, right. But if you're looking back, if you're looking at like the lineages that survived, right? And you're going back to where they diverged, like in the Tristan da Cunha, right? Like you're looking at where they diverged. You're you're the ones that died out are not going to even be part of that, right? So like
Exactly, and that's why the substitution rate is slower, because you have removed some subset of the mutations that occurred. Yeah, exactly.
okay, well, I did put that as one of the explanations. Like if I don't know if you were watching the whole thing, but I'll pull my slides up again because I put that in
Mm-hmm.
my thing as a possibility,
Mm-hmm.
right? As one of the possibilities that could help reconcile the discrepancies between the phylogenetic and pedigree rates. So, you know, I I recognize that that's one of the explanations given.
Yeah, and that's again, this is like a direct documentation of it. I mean, the Tristan da Cunha is just one of the studies, but it's very recent, and it's like a 1816. Like we know the date too, very clearly. So I really like that one. But that's the point, right? We like background selection is a real phenomenon. The mitochondrial DNA is non-recombining. Therefore, you're going to reduce the fixation rate of the neutral variation in the control region due to the harmful mutations that occur in the 90% of the genome that is protein coding. That's it. And therefore, that pushes the date of the most recent common ancestor backwards in time. That's a separate problem from the Neanderthal thing we talked about.
Right.
That's
But
its
are
own.
you go ahead.
No, I was just saying it's a totally separate invalidation of the young Earth model.
Okay, are you saying then there is no more discrepancy between the phylogenetic rates and the pedigree rates? Like we've explained it.
Yes, yes. We have explained this, and the papers you're citing, what was it? Parsons is from what 97 or whatever. I mean, there's literally a paper in 2009 that draws this curve that says like here's what the curve looks like, the fixation rate curve. Here's what it looks like if you account for selection, and it's calibrated, which I know creationists think is a dirty word, but calibration is just you have a fixed known thing and you anchor your data on that fixed known thing. So you can calibrate it based on a bunch of fixed known events and then draw your nice curve. And yes, that resolves the discrepancy. It's only a discrepancy if you assume that the mutation rate should equal the substitution rate, but like that's silly. Nobody thinks that.
Okay, so if it was resolved in 2009, then why are there papers still being published in 2024 trying to resolve it?
I don't know, because people are wrong. Like you wave the paper in Chris's face before, and we're like, "Do you disagree with deep?" Like, yeah, scientists disagree about stuff all the time, and like most people don't have time to read most papers. So people are doing, mitochondrial diversity studies, and they're like, "Oh, look at all this diversity in this population," or whatever it is that they're show. Look at this fast mutation rate in this pedigree, and they throw in parts of it. Oh, if you wind this clock backwards, you get 6,000 years. Okay, population geneticists don't do that because that's not because you have to account for other factors, right? You can't just use a single generation rate.
Right, but I mean, are you saying these population geneticists are so incompetent that in 2015, 2000, 24, they're still doing studies to try to reconcile the phylogenetic and pedigree rates?
Wouldn't surprise me. There's people repeating other people's work all the time. Yeah, that happens all the time. Where people, publish a study, it's like actually this was already dealt with, but it's not all papers are famous. Most papers don't get read by very many people. So, like, yeah, that's a thing that happens. If you have a specific paper you're thinking of where they specifically say, we're trying to reconcile this, that'd be great. It could also be the case that they read the 2009 paper and were like, we think they're doing this the wrong way. Here's the right way to do it.
Right. And let me grab the one I'm thinking about from 2024 and just see what they're saying about it. So yeah, this is Arna Detour. I'm probably butchering that last name, but this is from 2024, and it says the rate of mitochondrial mutation typically cited in the literature is around 20 times higher than that of the sorry, go on.
Mutation, yeah. The mutation rate is higher, yes.
Right. So, yeah, and it says, based on phylogenetic inference from differences between the sequences with a known divergence time. Pedigree-based estimates are substantially higher than those inferred from phylogenies, both in humans and other species, but are based on a limited number of mitochondrial transmissions and have relatively wide confidence intervals. Go ahead.
Yes, that's a bad thing. Wide confidence intervals are a bad thing.
Oh, yeah, I'm thinking because if you have a wide interval, then you're not very confident.
Right. So what you just read agrees with what I've been saying. We can go through it line by line if you want to read it again, like a couple words at a time.
How does it go with what you're saying?
Read it again. We'll go a little bit by little bit.
All right. The entire thing, or just what I said about pedigree based?
Start from the beginning. The 20 times faster bit.
Okay. The rate of mitochondrial DNA mutation typically cited in the literature is around 20 times higher than that of the nuclear genome based on phylogenetic inference from differences between sequences with a known divergence time.
Yes, hold that right there. So mutation rate, not substitution rate. Two different things. The mutation rate is very fast. The substitution rate is not. The mitochondria has a faster mutation rate than the nuclear DNA. Yes.
Okay. Pedigree-based estimates are substantially higher than those inferred from phylogenies.
Yes, because pedigrees don't account for selection and use somatic mutations. Yes, that is true.
Okay. So you're saying,
so what was the next?
You're saying this person is quoting this, and
wait, was there
they're
one more
not
line,
accounting
though?
for any of that. They're like,
wait, maybe that person was using the words differently from how I understand those words, but the words that the person said right there, totally consistent with what I've been saying. Yes, actually, read the next sentence, the part with the wide confidence intervals or whatever.
Okay.
Do the next sentence.
Both in humans and other species, but are based on a limited number of mitochondrial DNA transmissions.
Boom, pause right there. So that's talking about pedigree studies, saying we're only looking at a limited number of transmissions, not over longer periods. Good.
Yes. And have relatively wide confidence intervals.
In other words, we don't have high confidence in those numbers. Yes. So when you use limited data sets and you're looking at the mitochondrial mutation rate, right, in pedigrees, you get a higher rate of mutation with a very wide confidence interval. Yes, those things are all true. None of that supports the notion that you can use the mitochondria, the mutation rate, as a substitution rate. Do you see that is the case?
It doesn't say anything about that yet. Okay, but this is setting up the problem so that the study can resolve some of this, right? And so this study is saying, look, it's based on a limited number of mitochondrial DNA transmissions. And then this study is based on 116,000 mother-child transmissions.
Okay,
right?
but that's still just
it's
one
basically
generation.
Saying, but now we're doing this study that's extensive. It's not a limited number. It's extensive and it's deep.
Read the next paragraph.
Various explanations have been proposed to account for the difference between phylogenetic and pedigree-based mutation rates.
Yeah.
So this is 2024. There's still a difference.
Yes, that's what. Do you understand? Like, is this in the introduction or the abstract?
This is in the introduction.
This is exactly. So they're doing the lit review part. They're saying, here's a thing that people have seen, right? This discrepancy. There have been a bunch of explanations proposed to explain it. That's the part of the paper that we're doing here, right?
Yes.
So what do they say about pedigree mutation rates in that paragraph?
Okay. One is their, this is their explanation. One is recurrent mitochondrial DNA mutations at highly mutable sites that are detected in pedigrees but missing in phylogenies, where each branch typically spans hundreds or thousands of generations.
Okay. Yeah. So you
Yeah.
have, so that's saturation, right? Where you have multiple hits at the same site, which I don't think that's that big a deal, but sure. I mean, given the size of the control region, sure, could be, maybe.
Okay. Yeah. And if we keep going with this, they are setting up a lot of the problems that they are going to attempt to
Right.
resolve in the
Which
study.
is
Right.
my point, and I'm glad you pointed that out
Right.
because this is my point. Why quote from that part of the paper as though it's like the important part if they're just setting up the problems they're going to solve?
Well, because the whole point of me quoting from this is to say that this problem hasn't been resolved. This is still an ongoing thing in 2024. You were kind of making it sound like, oh, we figured this out back in 2009.
I mean, we
And
figured
I'm
it out
saying,
before
if we
then
figured this back out in 2009, why are we still trying to figure it out in 2024?
because scientists disagree and they're constantly refining like our understanding. I don't know why that's like there's never just like one paper on a topic and then it's done. Like that just isn't how it works. I don't know why that's surprising. And also, you're
Right. No.
always going to, and as a matter of just like writing in science, you got to sell it, right? So you're always going to write your paper to be like, this is a problem. Here's how I solved it. Even if it's actually a problem that there's already an answer to.
Okay.
Like that's
Well,
just that's just how papers are written. And what you ought to be doing is quoting, and this is just not you, this is creationist like in general. Instead of just quoting the abstract, the intro, if you're going to pick a quote, go to the discussion at the end where they're summarizing
let's
their
go.
findings in the context of what we know.
Yeah.
That's the part
Well, let's do that.
where we're going to see their conclusions, right? Do you have a link to this that I can pull it up? Because I didn't catch the author's name when you said it a little while ago.
Yeah. I mean, I really hate trying to search for stuff because I only have one screen. So, but I'll
Well,
try to
can
get
you?
it.
I can pull this up and I can like explain it if I can pull it up. I probably have the
Okay,
paper. I
look
just don't
it
know
up
what it is.
under Helgeson 2024.
Oh, it's Helgeson. I have that
Yes.
paper. Yeah, it's Helgeson.
Okay.
Okay. Yep, I got that one. Uh-huh. Where's Helgeson? I'm spelling it wrong. There it is. Wait, this is 20, I get Helgeson 2015? Is that the one
Okay,
you're talking about?
that's an older Helgeson one. Helgeson is just one of the names on this one. So I
Oh,
mentioned the first name on the paper, which is like Ardatur, Arna.
all right, whatever. It doesn't matter. Anyway,
Okay.
it's what you're quoting at me is the here's the problem we're going to solve, not the here's the solution part of the paper. And if we're going to do
Yes.
this exercise honestly, you need to look at the solutions, not the statement of the problem, right? Now, I
Yes.
know what you're
No,
doing
well,
is to point out that the earlier paper didn't solve the problem. I get that. But engage with that paper on the merits, is what I'm saying.
right. And I have engaged with this paper on the merits. I only
The
picked that
09 one?
word. I only picked the what?
The paper I referenced, the 09, the correcting for purifying selection paper?
Yes, I did. I get, look, I don't remember all the details of all these papers off the top of my head, but I did read all of these papers that I'm mentioning. I have read them and paid attention to
Okay.
what they were doing. Okay. So I don't remember the exact thing. I have the 2009 paper right here if we want to talk
Oh, I
about
found
it.
the paper. Here you go. Thanks, Chris.
Okay. So let me get that 2009 paper.
Well, look, the whole point is that background, like, we don't have to go through these papers line by line. Background selection is a real phenomenon that exists. And when I explained it a few minutes ago, you're like, oh, okay, I could see how that could work. That's it. That's all there is to it. If we accept that that mechanism is a real thing, then the mutation rate doesn't equal the substitution rate, even in the control region. And that's the ballgame.
Well, it's the ball game for what? What do you mean by that? Like,
It invalidates the 6,000 to 8,000 year time to most recent common ancestor for the mitochondrial DNA.
well, it's a possible explanation, right? But, you know, obviously people are still talking about this. So
We agree.
it's not
Okay,
settled.
let's
It's
go
not
through it
settled.
little bit by little bit. We agree that the most of the mitochondrial DNA experiences very strong purifying selection. We agree on that.
Yes.
We agree that because it's essentially a bacterial chromosome, it's non-recombining.
Yes.
And we agree that if you select out a mutation in the coding region, you also lose whatever mutations are present in the control region.
Yes, yes.
Okay, that's background selection. That's it. Then
Okay.
we agree, and the necessary mathematical consequences of that is that the mutation rate and the substitution rate don't equal each other. That's it. That's the whole argument.
Okay. Is that enough, though? Is that
Yes.
enough to bridge the gap between 600 generation, one mutation per 600 generations, and
Why?
one mutation per 25 to 40 generations?
Why are we doing this in terms of mutations per generation rather than time to most recent common ancestor? Because mutations is just they occur, right? A mutation is when the change happens, right? The time to most recent common ancestor is calculated based on the divergence. How long
Okay.
would it take to accumulate the differences?
Okay, so does just the effect of neutral, can you, from your assessment of background selection, you can definitively say that the gap goes from common ancestor 6,500 years ago to common ancestor 6 million
60
years
to
ago?
200,000, yes. Definitively 100% yes. And we can do that without any
Okay, so you're
evolutionary
not
assumptions at
doing
all.
chimp, you're not doing it,
No,
so
nope.
you're
You can
not
do this
doing
based.
human chimp divergence.
Nope, you can do this based on Anne of York. I forget the relationship to Richard, like Richard III's sister or whoever that they used as the anchoring point for that study. Like, and that's from the 1400s, right? You don't. We agree on when Anne of York lived, right? So you don't have to have any evolutionary assumptions in order to make this math work. You just look at the data with known times within the last few hundred years, and you get the slow rate or the phylogenetic rate, whatever you want to call it.
So are you saying that rate based on, whoever of York is like in the 1400s can take you back to common ancestor of human and chimp at 6 million years?
If you were to use that substitution rate that you calculate using Anne of York going to the two lineages that we've determined in the present, the two matrilineal lineages from Anne of York in the 1400s, if you take that rate, you get the human mitochondrial most recent common ancestor. I forget the exact number for that one, but it's outside of 60,000 years ago, right? Whatever it is. Now, I don't think that study applied that rate outside of Homo sapiens. So I can't say what the number would be if you applied it to human chimp common ancestry. But I want to be clear, if they had done that, or if I was to do that, that is not an evolutionary assumption because the causation is going the other way, right? The inference is going backwards, not forwards.
Okay, but the reason I'm bringing up this human chimp ancestry thing is because so many of these papers
Doesn't
talk
matter.
about how they
Yeah.
calculated the rate
Mhm.
from the human chimp common ancestor split.
And my point is you don't have to do that. You can ignore that. That's perfectly robust methodology, perfectly valid calculations. We can ignore that. We can do this within documented, recorded human history and get a date for mitochondrial Eve that's at least 60,000 years ago.
Okay. And what are the studies that show that?
So possibly the most perfect combination of author and study in the history of science is that the Richard III study. The first author's name is King. It's King et al. 2014. I think it's like identification of the remains of Richard III.
Okay.
Uh,
I will
there's
look into that.
there's the Norfolk Island study. There's the Tristan da Cunha one, which is Sudyal, whatever year that was. None of these are based on any evolutionary assumptions because we're talking about documented, recorded events within human history within the last couple hundred to couple thousand years. I think in some cases, in the '09 paper, they used the Canary Islands and Vanuatu, which were settled, I want to say, 2,000 and 3,000 years ago. Right?
Okay,
Again,
wait, hold up. First of all, Sudyal didn't, all that paper determined is that the mutation rate would be more than 1 in 36 generations. So I don't think that gets you back to the timeline
oh, it
that you're
does.
saying.
Because well, let's look. It's because you can directly look at the variation. I'm just going to do some real quick math here. Let's pick 1 in 30 generations, right? Because that's I know raw mat
Okay.
likes that number. So 120 differences times 30 generations per difference, right? Times 20 years per generation. And then let's get that and then divide it in half because you get mutations along both lineages. When you do that math, which is how raw mat does it, which to be clear is wrong, but when you do it raw mat's way of doing it, you get 36,000 years,
Okay.
which is
I
six
mean,
times the young Earth timeline.
now that's a little strange for me since Parsons said the most recent common ancestor would be 6,500 years based
Because
on one mutation in 33 generations.
because he was only using the control region. But again, it's non-recombining, so you have to use the whole mitochondrial genome because it's non-recombining.
Wait a minute. Hold up. And this is I sort of pushed back on this earlier and you gave your explanation, but
How can
it's
you?
not
What's
a
the
good
mechanism?
explanation.
Well,
It's
what's the
not a good
mechanism?
explanation. No, wait, let me respond to this and tell
Yeah,
you why it's not
please,
a good
because it's
explanation.
non-recombining. So what's the mechanism to count them separately?
Okay. The point is that what most of these studies are doing is testing within the control region. So if you're
Right,
paying attention to the whole one, then you have to deal with a lot of other factors. But if
right.
you narrow in on the control region, which it's not my idea, it's all of these geneticists that are doing this work. They're
Because
choosing to
I can
use the
explain
control
why they
region.
do that if you want. I can explain why they do that.
Okay.
Because it mutates, you have more mutations in the control region. Therefore, when you're looking at short-term things like a pedigree, you get more variation and you can see more fine-tuned differences. Whereas if you're using the coding region, there's much less variation there. There's between 50 and 80% of the mitochondrial DNA is identical across all humans. So comparing across those when you're looking at like familial relationships is pointless. There's no differences within the family, right? So you're only looking so these studies, sequencing is expensive, PCR is expensive, like hone in on the part that's going to be useful. This is the same reason that when you're doing phylogenetics, you have to use different regions of the genome based on the things you're comparing. You can't use like ribosomes to compare apes because they're all identical, but you can use ribosomes to compare apes to bacteria, right? Within a family, sorry, just within a family, there's going to be so little variation within like the coding region that it's pointless to use it. But across longer time frames, you can build up the mutations there. Very few of them, but they're still there.
Okay, but that's not the only reason that they're using that region. They're using it because it is believed to be neutral so that it's not under strong selection and so it can get a more accurate rate. That's why they're using it.
Well,
So you're
it's a
saying,
faster
no, we should
rate.
go back to using this one that has all these variables. And
Yes, because like yes,
that's
like
not
why
what
would
most
you?
of these studies are doing.
Well, because most of the studies aren't. That's so. Two things here. One, if we go back a few minutes, we agreed on how background selection works, and like, there's only three things you need, right? There's selection in the one region, mutations in
Right.
the other region, and linkage between them. Like, that's background selection. We agree that that's a real thing, right? So now the question isn't, does that exist? The question is, how does that affect the rate? Most of these studies, they're not calculating the time to most recent common ancestor. They're saying, hey, look at this mutation rate. If you were to extrapolate this backwards, here's the time to most recent common ancestor. But no one does it that way because there's selection happening. Not in one
Right.
generation.
Okay, but here's the problem with that and with what were our empirical observations
No,
is
no, hang
that
on. I gotta, no, 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 because the things that I'm bringing up are also empirical observations. The Anne of York, Richard III study, that is an empirical observation. Tristan da Cunha, that's an empirical observation. So you can't say, oh, we creationists use the empirical studies and you use the inferred studies. No, 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 no. These are all directly observed studies that we're talking about.
okay, but the Tristan da Cunha one only gets you, the possibility that it's 3 mutations less than Parsons found, right? So it doesn't take you to your timeline that
Yes,
you
it
want.
does.
I don't know about all the math that
It
you're doing.
absolutely
Okay,
does.
But you're saying so 1 in 33 mutations would take you to 6,500 years as the most recent common
Only for the
ancestor.
only for the control. Only for the control.
Okay, but
can you explain to me why over long periods of time, which is anything outside of like 2 or 3 generations, what I'm saying is long, I don't mean millions, I mean anything outside of 2 or 3 generations, can you explain mechanistically why we can exclude 90% of the mitochondrial DNA from consideration, considering that it is non-recombining? Now, in a nuclear chromosome, you pick a region and go because it recombines. All good. You can't do that in the mitochondria, right? It's non-recombining. So on what basis can we say we're only going to take the control region and we're going to extrapolate that backwards and we're going to ignore the other 90%?
Because of your favorite concept, purifying selection. So we already know, right?
But we agreed it affects that.
Coding regions, if you get a mutation there, you could die or be harmed. So you are not going to be reproducing and passing on. Now, you're saying this linkage, this background selection so that'll take away mutations.
I didn't say that. We agreed on that. We agreed that that's the case. To be clear.
I agreed that might be an explanation, right?
Well, okay, let's go through it. Let's just check it again.
But hang on.
No, I want to see if we agree on it, because 20 minutes ago we did, right? So there's the coding region is highly constrained, right? And it's linked to.
You don't need to re-explain it.
We agreed. You're saying like now you're skeptical of it though. Like we agreed that this is a thing that happens.
I have tried 3 times to tell you why it goes against, like why it doesn't work for our empirical observations.
But it does.
Mutations. I'm trying to tell you, but you're not willing to listen. Look, just let me say what I'm going to say. You can argue with it after I say it, okay? But the reason that background selection probably does not make a difference in the studies that we're looking at, okay, is because we are observing the ones who survived.
Yeah,
with
exactly.
The mutations. They didn't die out.
Thank you.
So that linkage didn't go together. So
no, it did. It's just no, Rebecca. It's not that they somehow magically became unlinked. It's that in the one generation, like you said before, you're only seeing the kids who survived. And so you're not seeing you're right that we're not seeing the effects of selection. It's because it's a short pedigree. That's the point. When you expand the pedigree back 3, 5, 10 generations, a couple hundred years, now you see the effects of selection, and that's why you get the slower rate. You explained this perfectly, like a little while ago.
Actually, that seems like we would have a higher mutation rate. It seems like it would work in the opposite direction of what you're wanting to work in. Because like, let's say these, mutations are linked with, deleterious mutations, and therefore they're getting selected against. That means we're counting a slower mutation rate than what we should be counting. That means we've lost mutations that we should be counting. So the mutation rate should be higher.
No, because we don't use mutation rate to calculate time to most recent common ancestor. We use substitution rate.
I know, but the whole argument is whether or not this is like, we're talking about why are we using these different regions? In the control region, in these hypervariable regions, it's supposed to be neutral. They believe it is neutral. Right. So now they're saying
yes.
Possibly it's not as neutral as we thought.
Mutations in that region are generally neutral, which is why we see more variation in there. The problem is not selection on the control region. The problem is background selection, because it's linked to the rest of the mitochondrial DNA, which, remember, is 90% of the mitochondria. So assuming, which is a valid assumption, that mutations are approximately equally likely to occur anywhere in the mitochondrial DNA, approximately 9 out of 10 mutations are going to occur outside of the control region. We don't see all that variation outside of the control region because you have strong purifying selection there. Because those 2 regions are linked, because the DNA is non-recombining, you also lose variation, like we agreed on, from the control region. And that slows down the rate of accumulation.
So that's why you like the whole thing, because it slows it down to where you need it to be.
No, it's no. Oh my God. No,
Okay.
you are putting the cart before the horse, and you're assuming that I'm trying to support a position and backfilling rationale to do it. What I'm actually doing is taking into account the factors you need to take into account. You've said repeatedly that when you use the whole genome, you need to take into account all of these other factors. Yes, because those factors are operating over the time periods that we're both concerned with, which is within the last 10,000 years, right?
Which is why most of these studies don't like to do the entire mitochondrial DNA, because there's too many variations, too many like factors that you have to account for. So why are you not okay with using the one that's most controlled, most neutral, the one that we don't have to have all that, like, you know, I mean, and
Because
that's the other thing, is that we actually know that we've observed that these tick at different rates, basically. So
no,
we're
they don't.
trying to pick the one that's the most neutral. So why aren't you okay with using that?
I am not okay with cherry picking part of a DNA molecule that is linked to the rest of the DNA molecule. Rather than ask me, why should we use the whole mitochondrial DNA, creationists need to justify basing their rate on 10% of the mitochondrial DNA instead of the whole thing.
Well, I think I did just justify it, but it's not creationists. It's the geneticists that are doing these studies. And they're saying specifically why they use that region.
Yeah, because they're looking at variation within a family. Yeah.
So are you saying, like, you're not arguing with me, right? You're arguing with these scientists
I'm
and their
arguing
choice to use that
I am
region.
arguing with the interpretation of their data that mitochondrial Eve existed within the last 10,000 years.
Okay, and I mean, actually, I'm not saying they think mitochondrial Eve lived
Right.
that shortly ago. I admit
And they
they don't
explicitly
accept
say their
that because
data
of their
doesn't support that.
evolutionary assumptions.
And to be clear, that the authors in question here explicitly say that their data does not support a recent mitochondrial Eve. Like, to be clear, they are saying that creationists misinterpret our data. Some of them say that explicitly.
I'm just reading the words that
Mm-hmm.
they said with no interpretation. I'm saying, look, these are the words they
Well,
said.
you're reading some of the
They said,
words.
which
You're reading
I'm
some
doing
of the
what?
words.
I read the parts where they say, clearly we can't accept this, right? Like they said, this Parson said,
Did you read the part with
this
the
would,
reasons why?
because it doesn't match up with the
Nope.
evolutionary timeline.
Nope. That's not why. No.
Okay.
That's just dishonest to say that. They don't know. That's wrong. They say you read one of the excerpts before, and it said in the thing you read why this is not valid. And they said this is contradictory with these observations, with these
Yes.
observations. They didn't say, oh, we have to make sure it goes back 100,000 years. We said we have all this other data that points to this timeline. This singular calculation, if you were to do it, would contradict that. Is it likely that the one is wrong or all the rest is wrong? Right? That's what they're saying.
Right.
Right?
And it is
They're not doing what you're saying they're doing. That's
it's
dishonest.
my shortening of it to say it doesn't match with the evolutionary timeline. But that's the gist of what they're saying. Okay. And okay, if the evolutionary timeline is right, then okay, they're right to say that. And so I am challenging that the evolutionary timeline, I'm saying that's not what we should be following, even though that's what the authors of the paper
Okay.
still believe in.
The
Okay.
data that I talked about, ignore the evolutionary timeline. Doesn't matter. We all agree on these dates. And we agree on background selection. And you did a really good job earlier explaining why those deeper pedigrees get you the older dates. You did a really good job explaining it, like, I don't know, 30 or 40 minutes ago. Like, yeah. And like, those are the methods, yes. And when you do that, and you said, like, when you do, like, that's how it should be done. When you do that, what years do you get? And the answer is 60,000 to 200,000. Most of them in the 1 to 150 range.
Okay. Well, I think we've exhausted this topic. So, I mean, I don't have anything else to say about it.
I just want to say, go back and watch this because we agree on background selection. And like we agree on the mechanism. We went through it twice at least. If that is accurate, which we agree is a mechanism, then you cannot get mitochondrial Eve in the last 10,000 years. It causes those two rates to diverge from each other, mutation, substitution. Like, think on that.
Okay,
In addition to the
here's what I
Neanderthal thing.
agreed. Here's what I agreed to. Here's what I agreed to. Background selection exists,
Then
and
we're good.
it's a possible explanation that has been proposed to reconcile these dates.
Well,
What I don't accept is that background selection has explained it all. There's nothing further to see here. Okay, because if that's true, then why are we still doing studies on this? Okay, so
I mean, the answer is because
obviously,
scientists don't stop.
okay,
Like,
well,
keep going.
I mean, but they usually try to find things that still have problems to work on, right? Sure. So that's the part that we disagree on.
And well, our understanding of mitochondrial, like, genealogy is certainly incomplete. No one thinks it's complete, so why wouldn't you keep doing studies on this? These types of studies inform all sorts of other things, like, I mean, everything from like disease treatment and transmission to archaeology, right? And like, does this match with the histories that we think we know? Like, there's all tons of reasons why you would keep doing this stuff that have nothing to do with any kind of uncertainty about the mitochondrial time to most recent common ancestor.
Okay. Well, I'll let you keep the last word on that. And I will say I'm very happy with this conversation because I don't know, you've had a lot of negative things to say about me lately, so I'm glad we were able to have a friendly conversation.
I'm glad we had this conversation too. This was fun, and I hope everyone watching enjoyed that chat. I've been following the chat. A bunch of you were way off base, and if any of you want to talk to me about it, email me, because I'm happy to go through this with anybody.
All right. Well, thank you everybody for watching, and I am going to shut it down now because we've been going for more than
It's
2
late.
hours. So thank you for everybody who came on. Take care.
So that was that conversation, folks. Like I said, I hope you enjoyed that and or learned something from it. The key takeaways that I hope everyone finds are that background selection is, in addition to several other problems, kind of the thing that invalidates the young Earth calculations when it comes to the mitochondrial time to most recent common ancestor, even if you only want to cherry pick the control region, which is approximately 10% of the genome. Even if you do that, you can't escape the selection that operates over generations due to the linkage with the highly constrained 90% of the genome that experiences strong purifying selection. So any mutations that occur in the control region still ultimately subject to selection via background selection. So I hope that got across. It seemed to get across for like just a second. Do I expect a long-term change in Rebecca's thinking on this? No, but it did, I think, just got across for a second there. So yeah, I'll take it. Anyway, I hope that conversation was valuable for somebody watching. Thank you for watching. Before you go, please remember to hit like, subscribe, comment, all the algorithm-friendly things. Thank you again for watching, and don't get fooled.